welcome back everybody online. Please feel free to ask a question whenever. Thanks very much.
Great. So let's see. We're going to talk about examples of this picture. So we're going to take, if gamma is the multiplicative form or group law, and then let's take it over FP. Okay. Remember, this has height 1. Okay. So then the automorphisms of gamma are just actually isomorphic to the units in the p-adics, it turns out. Okay, so for every unit, there's a way to write a power series that commutes with the multiplicative form or group law. And there's a lift to the following ring. So if I take our FP, let's call it gamma 1, and let's note that this is the formal group law of our K1. So this ring is isomorphic to, so if I just do the ungraded setting, I'll just get a ZP, okay? But if I'm in the graded setting, this ring is isomorphic to the p-adic integers adjoin a unit U in degree 2. And let's say just the degree of U is equal to 2. And note that this is the coefficients of P-complete K theory. Okay. All right. Next. So, and this whole setup gives us an action of ZP star on this ring. Okay. And this action is going to correspond to the action of the Adams operations on the homotopy of P-complete K theory, it turns out. Okay. And in fact, there's going to be, in the next board, I'm going to give a procedure for defining a homology theory given this kind of data, and we're going to be recovering P-complete K theory from that product, from that setup. So let me go over that. So for RK gamma, the universal deformation ring, the following, I can take X and I can do the following thing. So let's see. Let me say, I need to say one more thing first. So the formal group law of K gamma is classified by map, by ring map from mu star K gamma. Okay, so let's see. Remember when I first talked about formal group laws, I talked about how mu had the universal formal group law, and I said that every formal group law, for every formal group law, there'd be a ring homomorphism such that if I apply this to the mu formal group law, I get the formal group law I wanted. Okay, so RK gamma is an mu star module, right? It's an mu star algebra, but so it gets a module structure. Okay, so now here's a theorem. This is Weber, but producing the theories I'm about to produce, this way was something that was noted by Morava. So the map, so if I take a spectrum and I do the following thing. I take this ring and I tensor over mu star with the mu star homology of X. Okay, this is a cohomology theory. Okay, so what does that mean? It means that, it satisfies the Allenberg-Steenrod axioms. Okay. Okay, so what's difficult here? So the crux is the only axiom that causes a problem is exactness. Okay, and in general, you're like, okay, if I want to do a process like this and preserve exactness, so one condition you might ask is that this ring be flat over that. That would certainly be sufficient, but that would be an extremely rigid condition, and in fact, you wouldn't get that. If that was the condition you needed, then you would only get homology theories that are like not that far from mu, basically. Okay, so here it turns out that what Landweber showed is that there's another criterion that's not as difficult to meet as flatness that guarantees that this is a cohomology theory. Okay, and so you can produce cohomology theories this way, and then I'm going to say a couple more things, and so by Brown representability, there's a spectrum EK gamma, which is called which represents this theory. Okay, and the spectrum is called Morava E theory. Okay, so actually sometimes it's called Lubin-Tate theory or Morava E theory. Okay. Okay, let's go back to here. And then to finish this example, if we go here, so E FP gamma 1, this is P-complete K theory. Okay, so we can reproduce P-complete K theory this way. Let me state the criterion. Okay, so the thing that you need to check is called the Landweber criterion. Yes, this one here. Yeah. Maybe I'll say one more thing. Line of sight. I'm going to write one more thing. Is the action of, and I'm going to say a couple more things about that before we can make sense of this. I said, I produced a homology theory from this. I had an action on the homotopy. It doesn't mean I get an action on the spectrum, but I'll say something that gives it to us in a second. Okay, so now let's talk about the criterion. So if S is a ring with, okay, so I'm just going to think of S as a ring in degree 0, and with ring homomorphism. So I'm going to make it periodic. Then S X goes to S tensored over mu star of mu star of x is a homology theory if for all p, so p and then the image of v1, which we usually just call v1, that I called it phi. The image of v2 is a regular sequence. Okay, so this is a totally algebraic condition. Okay, so remember we had our VIs for each P, we had a collection of VIs in the mu star homology. And if for each P, this sequence, the image of that sequence in here is a regular sequence, then this is going to be a homology theory. This is weaker than flatness. Okay, but really it corresponds to some map being flat. It corresponds to like really what you need is not flatness over like mu star, but you need flatness over the moduli stack of formal groups, and this is equivalent to that flatness. I don't want to say more about that, but like there's a geometric reason why that's the right reason, and you can read about that in that Lurie's notes present this material this way. So that's I like that reference for that. Okay, so you can produce other series with this criterion as well. So I'll focus on Morava E theory for the rest of the lecture, but I just wanted to note that an example of such a thing, such a ring that has this property is I can take mu star. I want to take a mu localized at P. Let's take the homotopy groups of this thing. Let's remember that this was this. Okay. Okay, so now I can take this thing and I want to mod out. Let's mod out by all the BIs. Where did I call them B or T? I think I called them T. Let's mod out by the TIs where I is not P to the K minus 1 for K for 0 as an N. Okay, so we mod out by this one. So if I mod out by this, what am I going to get? I'm going to get Z localized at P, and then I'm going to only get the first. If you think about what this criterion means, is I've only kept the first VIs. Okay. And then I can invert VN. Okay, let's call this thing En star. Okay. So you can check as an exercise that, so there's an obvious map from mu star to En star that this is Landweber exact. Okay, so it satisfies this criteria. And so En star of x, my base change is a homology theory. And this is represented by a spectrum En called the Johnson-Wilson spectra. So it's yeah, that person. Okay, and the reason this one is like a lot more concrete given what we've done, right? So this is a construction we've gotten used to mu star, and this is how we got the Morava K theories, right? What we did for Morava K theory is we killed everybody except for Vn, and then inverted Vn. Okay, so these are very closely related to sort of moves we've done before, and this is like if you want to test your understanding, you can check that it satisfies this criteria. And this one relates to our story from before that E1, well, if I take K theory and I localize at P, well, it turns out that's not going to be quite E1 because I would only have V1 here, and V1 has the wrong degree, right? V1 is 2p minus 1, and the bot class is in degree 2. But we've seen this before. We just take fixed points with respect to the unit in the Z mod P in the atoms operation. So this sits inside, it's a direct sum n of P local K theory. Okay. So similarly, these EN theories, they're somehow so this one feels quite concrete. You know, I gave you a formula for what the homology theory is. Okay, you just have to understand NU star. These ENs came from this deformation theory. They feel a lot more abstract, but it turns out that they're very close to these Morava, to the Johnson-Wilson theories. Okay, so the ENs, sorry, I didn't say EK gamma. Okay, so now let me make a definition. Okay, so let's let EN be E. I was saying EN, but I didn't define it. So here I want to do K. It could be this or this. There's two versions, and they're both good. So now I'm going to take the formal group law for Morava Kn. I'll call this we're going to call this Morava E theory. N. Okay, so let me make maybe like people tend to call these guys more general for general gamma K. They tend to call them Lewin-Tate theories, but I'm going to save the name Morava E theory for this specific example. Okay, and the point is that if I do pi star of En, okay, so what is it going to be? I'm going to get the vid vectors on my field. Okay, I'll say something about that. So here, these are coefficients. They contain the p-adic. So this is a p-adic algebra. It's like you take the p-adic and you join a bunch of roots of unity. Okay, so it's not. These are some extensions of the p-adics. Okay, we're going to have n minus 1 variables and u plus or minus 1. And it turns out that there's going to be a map from this guy to this guy. And the VIs, you want to think of them as u to the, they just go to this thing. Okay, so okay, let me say something about that. Don't worry about those things, p-adic integers. If you don't know what the vid vectors are, just think p-adics, okay? So what did I do? I took like this ring here, and I added a u, which was in degree 2. The VIs, right? These had degree 2, p to the I minus 1, right? So I added a bunch of roots of the VIs, or like I made them more divisible, okay? Not roots, but I made them divisible. So I sort of added something that made the thing sort of more homogeneous, made it 2 periodic, okay? But that's not like, I'm just adding some, you know, so if you think about for Vn, right? Vn is invertible, and what did I do? For Vn, I literally added a root of it, okay? And a root of degree p to the n minus 1, that's co-prime to p. So you can imagine how that's in characteristic p, that's not going to be very drastic as a procedure. And then what did I do? So now I have power series instead of polynomial, so I completed. Okay? So what I'm trying to communicate is that En, if I take En, and I Kn localize it. Remember, I told you Kn is like mod P is like a completion up to some extension. This is Morava E theory. Okay, so in our K1 local example, we get, right, if I take E1, which is a sum n in P local K theory, and I K1 localize it, that's like taking roughly up to taking a bunch of copies of it. This is like taking P local K theory and K1 localize it. K1 localization is like P completing. So then I get P complete K theory. Okay, I'm going to push, it's going to disappear for a second, but it's going to go back. Okay. So we get versions of P local K theory, and then their completion now becomes K localization in this higher world, and we get the Morava E theories. So these are like the higher versions. These are higher versions of P local K theory, and these are higher versions of P complete K theory. Okay, that's how you want to think about these guys. All right, so let's see, which board am I going to erase? I'm going to erase my references. Okay, so now this is the Ghost-Hopkins-Miller theorem, and in more generality, it was generalized by Lurie, or parts of it were generalized by Lurie, and the theorem is that En is an E infinity ring, and the action of, okay, so now I'm going to define this to be the automorphism existing on the homotopy of En lifts to an action of En by E infinity ring maps. Okay, so having an action on homotopy groups is not the same as having an action on the spectrum. It's not the same as having a highly structured action on the spectrum. So this is saying like, and having a homotopy ring is not the same as having a highly structured ring, okay? So this theorem says that En is amazing, okay? It's the best kind of ring, it's E infinity, and the action of the Morava stabilizer group is as structured as you could hope for, okay? It's an E infinity action, okay? Okay, so if I could ask, I have an E infinity ring, I could ask about its automorphism as an E infinity ring. What do you think it's going to be? At height 1, right? We had the automorphisms were the atoms operations, and the atoms operations, remember I kept saying it's the automorphism of P complete K theory as an E infinity ring. Okay, and this is called, okay, so this guy is called the Morava stabilizer group. That's what you're asking about. Okay, so for example, G1, right, is the automorphism as an infinity ring of P complete K theory, and that's, it's okay. I'll keep this one. Cool. I'm kind of really out of sync with my boards. I'm sorry. I have to admit that I'm tired.
It's automatic that every number that effect theory is complex oriented.
Yeah, I didn't say it, but these are complex orientable theories. However, not every complex orientable theory is line-forever exact. So if you want something that doesn't satisfy this, Morava K theory does not. Okay, you'll note that here what did I do? I took pi star and then I did a bunch of things. When I defined Morava K-theory, I never took pi star. I did my cofibers in spectra, I inverted in spectra, and I did all these constructions that come from ring theory. I did them in the spectra, okay? And so, and I got a theory, and I didn't say what K star was. I didn't relate what K star of something was in relative to mu star. Here I did something different. I did a bunch of algebra on mu star, and then I defined the theory in terms, the values of the theory in terms of the values on mu star. This makes this particularly computable. If you can do mu star, then you can sort of play with that. So this is like different. That order is important. It's quite subtle. Maybe I'll write it as a warning, is that Kn is not Landweber exact. Yep, this is is that answer?
Okay.
Okay.
Okay, so I'm just wondering about this E infinity ring structure. So this like tensor product that I use to like define these things, can I think of like this S adjoin U plus or minus one? Can I think of this as just like an MU algebra if I want to, instead of like an MU star algebra?
Yeah, the S plus or minus one is mu star algebra, but but like mu star algebra.
And so I can't just like upgrade this like by like taking some inclusion and make it like an actual MU algebra and take this tensor product there?
Yeah, even if you have an MU algebra, if you start playing with things won't necessarily be in E infinity. So like En is an MU algebra, but it is not an E infinity ring.
Okay.
Yeah, BP is, maybe the better example is BP, the one where I just, even if I just split off, you know, I told you if you localize mu at P and then you get a wedge of this one theory called BP, the Brown-Peterson spectra, that is not E infinity. It's, I mean, Tyler Lawson gave the bound recently on how structured it is. There's a paper by him. Yeah. So it's more subtle. Yeah.
Okay, thank you.
Yeah.
Would anybody else like to ask a question? Would anybody online like to ask a question?
Yes, if I could jump in.
Please go ahead.
Quickly, yeah. Just in terms of rectifying sort of notation that varies, I think, flying around with some of the literature I've seen, I was just looking to confirm whether or not the Johnson-Wilson spectra and the Morava E theories are in the same Bausfield class, because when people localize it things, because I'm aware of the fact that I was fairly confident that was the case, but some people will sort of write Morava E theories, I think, with En in the notation of Johnson-Wilson, which sort of, I think varies based on how people's context wants to.
These are all the same Bausfield class.
Yep.
Yeah.
Fantastic, thank you. And I presume then really just pivoting to the sort of Landweber exactness point of view, that sort of the Morava E theories are the things that formally are nicer to be working with rather than these Johnson-Wilson spectra, which I presume are kind of historically a bit more relevant.
I mean, they both have their advantages and disadvantages. Yeah, it just kind of depends what you're trying to do. I think they're very closely related. I think they have their strengths and weaknesses.
Okay, yeah.
I prefer working with En, but it's just because that's just what I do. So yeah. Okay.
All right, thank you.
Yeah, and just for example, we had talked about this at height 1. This is, let's write it this way. So maybe I didn't say it exactly like that, but this was all in the in the first lecture, the first day, we talked about the various localization and I mentioned these kinds of things. Okay. Okay, so now we're in a good place. So what do we have now? Okay, so let me just do a little table. So we wanted, let's put it this way, to understand the K1 local sphere, we used KP and the action of ZP star on it. So now we have E1. Now this is G1, okay? And then what did we get? We got that, okay, maybe I should have given myself a little bit more space, but I'll do a Fred Cohen. Then we had that KP fixed points. Okay, so these are homotopy fixed points. I was a little bit glib about that. We had that this was our K1 local sphere, right? Okay, and finally, we also had that if I did KP tensored with KP and I K1 localized, then I got, it was K mod P at the time, but we saw that it's the same. Let me, and and actually the more concrete one is that it's P completion. This was maps from G1 into K. Okay, so we had these ingredients. I wrote them back on the board yesterday. Okay. Okay, so now we've got, so we have EN, we have GN. So we have an action. We can look up at fixed points and we can ask about what happens if I tensor EN with itself. Okay, then I can localize. I can ask what this is. Okay. All right, so let me write a theorem to that extent. So if I do as can, all right, so there's going to be a map to EN. Okay, so why is that? I'll motivate it later, but this thing is can local. Okay, remember how I told you how P complete K theory was K mod P local? We talked about that because it's an inverse limit of P local things. This is the same, okay? There's an inverse, this guy you can express as an inverse limit of things that are can local. This comes from the fact that I'm telling you it's like a completion of this Morava EN, okay? So let me not get into that, but there's a map. Because this is a ring, it has a map from S, and because it's can local, it factors through the can localization of S, okay? This is a GN pro Galois extension. So this is in the sense of Agnès in this context, okay? So what does that buy us? As can is the fixed points, okay? And if I can localize this guy, I'm going to get continuous map from GN to EN. And so there's a sense in which that if I choose to work with the field FP bar, right? I told you you could do FP bar or FP to the N, then EN, you want to think of it as, I'll put it in close. I'm not going to define what I mean, but it's like the algebraic closure. That's K. Okay. So in particular, this gives me a way to understand what the K local sphere was, right? Day 1, second lecture, I was like, okay, let's talk about the K1 local sphere, right? What does it mean to localize at K mod P, which is the same as K1? And we spent a whole lecture learning how to do that and seeing that it was the fixed point with respect to this action. And what I'm telling you today is that this is a general phenomena that happens at all heights if you know how to define your objects, okay? However, the difference is now you get En from this deformation theory, from the deformation theory of formal groups. Gn, the Adams operation, what is this? Its generalization. It's the automorphisms of a formal group of height n, okay? So, and this is how somehow the algebraic geometry of formal groups deeply informs chromatic homotopy theory and stable homotopy theory, okay? Because the prime localizations of the sphere spectrum are obtained by descending along a Galois extension from something that's coming from, like, totally constructed from algebraic geometry. If you think about how we constructed En, right? I did a bunch of algebra today, right? I did formal groups. You know, there was nothing. It was all like just classic algebra, and we got the ring R K gamma, right? We got the deformation ring, and then we used line Weber exactness. Like basically, we used mu star and just like, you know, this is a pretty algebraic process. Like what's not algebraic about that is just mu star, right? Okay, the mu star homology of the space. But like getting En from that was pretty algebraic, okay? And of course, now there are facts that tell you that you get this super highly structured gadget, that, you know, that this construction is very rigid and very beautiful, but like the actual producing it was very close to algebra. And then suddenly you get that, like, these guys, their Galois theory knows about the Can local sphere and the prime localization. It's just absolutely beautiful. Yeah.
It's hard to believe that you can actually compute with that gadget.
Yeah, okay. Agreed. Yeah. Okay, so now let's see. Let me just say one more. Let me say a remark. Okay, so I gave you no sense of what kind of group this Gn was, right? We know G1 is the p-adic unit and the p-adic integers. So this Gn, I mean, if you know some number theory, it's so Gn, you know, it contains, you know, Gn up to some Galois, so up to something that comes from this Galois group bit. Gn is a division, so it's the maximal order in a central QP division algebra of Hasse invariant. Okay. You're like, great. That helped. Right? Okay. So it's some algebraic, it's some group that like arithmetic geometers and people who study formal groups and number theory care about. Okay. So it doesn't really give you any sense. So but if you don't know what those words means, then you're not better off than you were before. Okay. But maybe Gn, the closest group that maybe I can get you to think of that is not Gn, but is close to it. And I'm only doing this because you told me about, because, but this group, okay? You can imagine this group, right? This is a profinite group. It's the inverse limit of GL of Z mod P to the K over K as a group, okay? So this group is that flavor. It's that kind of group. It's not that. It's not isomorphic. This is a different group. It's not a general linear group, but that's the kind of group it is. Okay, so it's a profinite. Gn is a, so what I'm going to say is a bit of a lie because I took some extension, but so up to stuff coming from the Galois extension K over FP. Okay, so the stuff that I added manually at the end, I just like threw it in and told you I'm not going to tell you about it. Okay, so up to that stuff, that's not hard to understand, which, you know, I took FP bar, right? So FP bar, this is a Z hat. Gn is is a p-adic compact p-adic analytic. Okay, so it's a compact p-adic Lie group. Another word people compact p-adic. Okay, so it's a nice topological group. Okay, and it's a manifold in the right world. Okay, when you're doing it, the manifold, if your charts now instead are obtained from replacing the completion of the rationals at the the Euclidean valuation to the completion of the rational at the p-adic valuation. Okay, so whenever you have the rational, we made a choice when we decided to think about the real numbers as the way we should think about manifolds, because we picked a valuation to complete at. Now, if you pick another one, this thing is a manifold. So this is very nice in its own world. It's just not a world that I think some people are very used to this world, but we're taught manifolds. We're talking about real manifolds and real geometry. So this is a very nice object in a different kind of universe, okay, in the p-adic world. Okay, so it's a nice group, but yeah, it's complicated. Okay, so now the next thing I want to say about this thing is, okay, so I want to do the following thing. So whenever we're trying to understand any kind of computations in homotopy theory, then we like to construct spectral sequences to do that. Okay, so I have the sphere, and this is a ring, so I can map the sphere to it. Okay, but now En is a ring, so I've got two ways to map it into here. Okay, so I can either take the unit of En and then tensor it with En on the right, or I can tensor it on the left, and it gives me two ways to map there, and those are typically different. Okay, and then I can keep going, right? Okay, all right, so I get some co-simplicial diagram, right? But now let's remember something. Let's say we can localize it. Okay, so we just can localize everything. This is the maps from GN. Okay, and I had to do continuous maps. Okay. Okay, I do this again. I have three tensors. If I decompose this one like that and then do it again, you're going to be able to identify this with and the next term and so on.
Intensely and localized.
Yeah, I said localize everything. Yeah. Okay. Okay, so you iterate that. What is this? What is the sequence that start with something and then it has maps from a group into it, and then maps from a group square into it, maps from a group cube into it? What does that remind you? Where'd you see that in your life? Yeah, it's when you're computing group cohomology, right? This is the Kovar complex. Okay, again in Bible, right? Okay, so this is the continuous. This is like a continuous. Okay, now I can localize and apply pi star, and I'm going to get a continuous version of a Kovar complex. Okay, and what that complex is going to compute is group cohomology. Okay, and it's going to be compute. So from this, I'm going to get, okay, so if I take, okay, I apply pi star, I sort of, I get an exact couple out of this, and I'm going to be computing, the complex I'm going to get is the continuous Kovar complex, and if I compute the D1 differential, I'm going to get continuous group cohomology. If you don't know what continuous group cohomology is, don't worry. Just like think group cohomology, it's fine. We're going to get that, okay? And now we have a spectral sequence from this thing, and it's going to converge to the homotopy groups of, well, the homotopy fixed points, but that's the Kant local sphere. Okay. And this is called the descent spectrum. This is the homotopy fixed point spectral sequence or the descent spectral sequence. Okay. And if we wanted to understand the Cannes local sphere, or say its homotopy groups, this is basically the best tool we have for doing that. Okay. All the computations that have been done, even if like they're Shimomura-Yabe or they're using EN and they can be repackaged into this spectral sequence.
That's a direct sum.
No.
Is that the whole chromatic thing? It's not.
So this,
Does that pick, what part of the chromatic bit does that pick up?
well, remember I put the chromatic factor square of, so that was one of the corners. And from that one, together with like a gluing data, I can get back the LN localizations, and those pick up, I mean, philosophically, those pick up VN periodic families. But then you have this inverse limit, right, which is that converges to the P local sphere. How that gets assembled into actually the homotopy groups of spheres is a big mystery. Yeah. Okay. Let me see what time it is.
Anytime you want it to be.
Oh, yeah. So let me state something, and then I'll decide after that what the last thing I'll do is. Okay, so let me just say that for n is equal to 1, computing this spectral sequence. So let me write first the abstract way to think about it, and then connect it to K-theory. Okay, so now what is this? This is the cohomology of the action of the atoms operation on the homotopy groups of P-complete K-theory, converging to the homotopy groups of the J spectrum. Okay. This is an exercise. It's one of the first exercises that my advisor gave me when I started working with them. Okay, so it's a really fun little exercise to do and to try to understand it. Of course, like maybe you need, remember I told you this is ZP U plus or minus 1. Okay, and I told you how this acted on that in one of my lectures, and then you can compute this. And except for the prime 2, this spectral sequence is just a long exact sequence. It's the long exact sequence corresponding to, remember we have the J spectrum, which ended up being our K1 local sphere, mapping to P-complete K-theory, like so, okay? So this is a cofiber spectra, so you can do the long exact sequence on homotopy groups, okay? The spectral sequence is a repackaging of that, okay? So,
Heuristically, is it correct to say that the image of J, right, you have the orthogonal group involved, etc. That is being replaced by the Morava stabilizer group?
I don't think it's the orthogonal group that's getting replaced.
I meant that, didn't mean that literally.
No, but even I understood, you meant it philosophically.
Theory, right? Associate. So the Morava stabilizer group is.
I mean, it's the Morava stabilizer group is the atoms operations. That's what you want to think of it.
Nice.
So you have K theory and you have the atoms operations on K theory. You have E theory and the Morava stabilizer group. That's the higher atoms operations.
What does the homotopy of the classifying space of the Morava stabilizer group detect?
That's the cohomology of the Morava stabilizer group with coefficients in ZP, say. It detects, I mean, let me write a theorem. Maybe, yeah. Oh, maybe, yeah. Okay, I'm gonna write something. I think you're gonna like it. Okay. oh, I don't like this board. Let's go. Okay, we're going to keep this one. Okay, so let me just say that, like, I could have done this with you if I had 10 more minutes, okay? But I'm going to leave it because it's good to, even though like you might be like, okay, I don't really know where to start, but to struggle to even know where to start and try to figure out what to do. Of course, there are tricks that make this a lot easier. I could do it in 10 minutes knowing all the tricks. Okay, so I'm not saying it's going to take you 10 minutes if you don't know what the tricks are, okay? But like getting to that point is a really good way to sort of absorb some of what happened, okay? Okay, so then I want to say the following. Okay, so then we have an updated goal is, what's this? Okay, but now this is huge and it's got some mysterious action, okay, hard to get our hands to. So maybe we should start with easier questions like, what's this? Okay, or what's this? Okay, so what is this? This is like the maximal like unwrap. Like this is you take the maximal unramified extension of the p-adic rational, and then you take the ring of integers in it. So it's like ZP adjoin all p to the kth minus 1 roots of unity. It's just some nice extension of the p-adics. Okay, so you can ask questions like this. Okay. All right. Well, how about then maybe we don't know. We know this in certain cases. We certainly don't know this, and we know this maybe like at height 2 for odd primes. We probably could do it for the prime 3 and the prime 2. We just got bored. There was more exciting things to do because it's quite gross and nasty and there's a lot, okay? But you could also ask, okay, with this one, instead of all the pi star, you can also just say, okay, what about just with pi 0, okay? So it turns out these are all hard. Okay, so one thing that we do know, and this is Morava using Lazard's theory, because this is a p-adic analytic group, Lazard has studied the cohomology of such thing, and one thing that we do know is that if we take the cohomology of Gn with, this is like putting ZP coefficients, FP bar, and we tensor with the rational, okay, then we get an exterior algebra. We get an exterior algebra over ZP on classes like so. Okay, this is where I said like maybe you're going to be. This has to do with the Lie algebra of this thing being. You can identify the Lie algebra of this thing rationally with the Lie algebra of the unitary group, and so then you recognize this cohomology. Okay. Okay, great. However, so we knew this for a long time, but here's a theorem, hard theorem from 2024. Yeah, I'm going to state the theorem under here. I take the cohomology of Gn with pi star of En, and I tensor with the rational. Then I get this answer. And that's it. Okay. And okay, so the hard part is this bit. Turns out, because if star is not 0, it's very easy to prove that all these groups are torsion, so they vanish. It's showing that this is an exterior algebra on these things. Okay. This uses a lot of recent developments in arithmetic geometry to prove this theorem. Okay, like it uses this two towers formalism. Okay, but as a consequence, we get that if we look at the K and local sphere, so we have this thing, it's an exterior algebra. We have this spectral sequence. I didn't tell you anything about the grading, but like this doesn't seem like a lot of stuff, right? This is very small. It turns out there's no, once you tensor with Q, there's no space for differentials. So what this thing does is if I tensor this spectral sequence with Q, I get the rationalization of this thing. So that's like taking K0, right? Because this is Q. I get that the rationalization of this thing is a wedge of suspensions of HQ indexed by, the monomials in here. Okay. So rationally, this is a beautiful answer. Okay. But this is the best general result we have.
Pretty funny, a spectral sequence where the E2 term is a lambda algebra.
On this pun, I think I will end here. I think I've said enough. The thing is, this is like this field, although like it's been around and there's been a lot of progress, especially a lot of progress recently, it's still really wide open. Okay, so we have predictions for all of these things. In fact, what do we think? And we know it for some. So recently somebody proved, it was Salch and Kong, that they proved that at big primes, this is also an exterior algebra on N generators. And then that implies with a couple some tricks in the rational answer that this is an exterior algebra. So now, and this is believed to be the same as that. So this is believed to also be an exterior N generators. Okay, you're like, oh, well, will the answer just be that then? Hell no. As soon as you put star here and you don't work rationally, blows up. The answer at height 2 is extremely hard to internalize. It's a very complicated answer. There's a lot going on. Homotopy theory is hella hard. So I'll end on that. Yeah.